welcome everyone to our session this afternoon about immutable server generation, the new app deployment. My name is Axel Fontaine. I live in Germany. It's actually my first time here in Atlanta. So it's I've had a lot of strange looks already on my very first day when I arrived here the day before yesterday, because Pratik was actually very nice and organized everything very well for us speakers, and so he said, well, you know, I got you the hotel booked and it's all taken care of. Just grab an UberX and you'll be there and no problem. So I thought, well, I don't need to do that. I can just take the public transportation like everybody else. So, well, there were some serious, how shall I call it, diversity issues while I was riding the public transportation. But that didn't matter too much. But what really shocked me that once I got off the bus, there was no sidewalk. I had to walk on the street with my suitcase to get here. So I had a lot of weird looks, but it was fun. I made it alive. So here we are for this afternoon session. So a few words about myself. So I'm the founder and CEO of a company called Boxfuse. We'll touch a bit upon that later during this talk. But I've been in the industry for quite a while. I've been here for more than 15 years. You don't get a large forehead like this overnight. You have to work on that. So I've done a lot of consultancy in the past. And through all these engagements and these assignments, I've always found that the intersection between development and operations has been a place where there's been a lot of inefficiency or a lot of potential to get better. And that kind of sparked my interest in this space and the continuous delivery space in particular. So for the last 4 years, I've been quite active in the speaking circuit, mostly in Europe, just because it's more convenient for me. I did have a chance to be at Java 1 last year, so that was good fun, and apparently a few people liked it because I got named the Java 1 rockstar, whatever that means, but that was fun. This is my Twitter handle. If you want to get in touch or give some feedback about the session, I'm always looking forward to hear some of that. The other thing I've been involved with, just lost my microphone. Sorry about that. I've got two of them wired up here, so it's a bit of a challenge, but we'll manage. So the other thing, also in the DevOps space, I've been involved with is my open source project Flyway for database migrations. Has anybody heard of Flyway? About a few of you. We'll touch a bit upon that today and a whole lot more about it tomorrow. There's a whole session in this very same room about it at 10:30 tomorrow, so just after the morning keynote. So if you want to learn a bit more about that, we'll talk about it tomorrow, but we'll touch upon it a bit today as well. As I said, I'm currently working for my own company here at Boxfuse, and we do have a reasonably large slot today. It's actually much larger than most of the slots we have in Europe. There, we usually have 50-minute slots. So you've got a lot of new material that's never been presented before. So some of that you'll be the very first ones to see. But it could also mean that we may have a couple of minutes at the end. So I will kindly ask you, if you have any questions, just hold on to them. And I'm sure we'll get around to answer them at the end. And if we run over, I'll be around in the hallway as well to answer more of them. So that should be fine. So let's start with a little story. My girlfriend is an engineer, and so just as me, she gets excited about all kinds of technological stuff. And recently we were changing some stuff in our living room, and one of the things that needed to be replaced was a lamp. And so she went shopping and came back very excited with something brand new, with a LED bulb. So it's just looks the same as a traditional lamp, except that instead of consuming 60 watts, it's consuming 10 watts, gives off the same amount of light, so that we've basically gone from a technology that is a heater that gives a bit of light to a light that gives a bit of heat. And so that's actually quite surprising to the touch when you first when it's been burning for an hour, you touch it and it's cool. So it's quite interesting. But She could have, for the purpose of this talk, she could have just as well come back with this, which I personally find much more exciting, because if you plug it into your socket, you can turn your living room into the local discotheque. So but I'm not sure she would have agreed to that choice. So we decided to leave it at that. And focus a bit of this. And actually, if we look at this picture here, the interesting part for this talk is actually the bottom part. It is not the part that lights up, it is this little screw, better known as the Edison screw. It has been around for a long time. Mr. Thomas himself has come up with this, so it's well over a century ago that first happened. But what he did manage to create with that was something very interesting. He brought us a simple, standard complying interface with a clear contract. So it allowed us for the first time to have something where we could just kind of screw it in and be done with it and separate a bunch of concerns. And so for now, we could stop worrying about how the electricity got produced. All we needed is something that we could screw in there, and we would then have lights. So we basically divided responsibilities between the electricity company and ourselves. It's a bit of an abstraction form that has stood the test of time very well, because really what this is undifferentiated heavy lifting. We don't really care whether that power has been produced by coal, by nuclear, or by solar or wind. For us, it's nicely abstracted away at 50 or 60 hertz, 110 or 240 volts. It doesn't really matter. We have a certain interface with a contract, and as long as we obey that contract, we are free to innovate here at the top any way we want. Whether we want the discotheque in our living room or not, that's how we choose it to be. Now, how does this relate to IT infrastructure? For that, let's first get to know each other a bit. So from the people in the room, who is currently running on-premise infrastructure where you have your own data center, your own servers, the whole shebang? Okay, so we've got a couple of people. Who's doing co-location, where basically you've got your servers in somebody else's data center? Okay, about 10, 15 hands, a bit more than on-premise. Who is renting root servers at some provider somewhere? The big names are OVH, Hetzner are quite big, where basically you just rent a server by the month somewhere. Nobody? One hand? Okay. And who's on the cloud? Okay, that's about the same number as what we had for co-location. That's about maybe 20%, a quarter of you. From those who are on the cloud, who's on AWS? Who's on something else? Okay, so we've got 2 rebels and the rest is on AWS. Okay. So, if we look at these different steps of our infrastructure and these different options, how did they evolve? Well, to be able to answer that question, we have to take our big time travel machine and go back to the exciting times of the 20th century. We had, of course, this guy running around and chasing the ghost. This apparently was how music was played, and this was how you would rewind it. So it was pretty exciting times. It's really not to be underestimated. And of course, we also had this guy. And he loved it when a plan came together. So when his plan was to get a server, this is how he would get about it. He would get on the phone, you know, the old style with the cords and all that, and he would call his good friend Michael. And he said, hey, Michael, I would like a server. Can you help me out? And Michael says, well, sure, I would love to do that. And a couple of weeks later, a pizza box would arrive in the mail, which would then eventually be put into a rack. You would screw it in and connect the network, the power, and then what? Well, you're not out of the woods just yet. So he gets on the phone again and calls a young criminal from the western coast of the United States, who then delivers him some criminal software, and we can install it, and from there on, basically, we start patching and updating it as we go along. So, if we kind of put these pieces together, we've got our software, we've got our hardware, and we've got our data center, the classic model for on-prem. And it turns out that this is actually pretty hard. If we look at the challenges we have to solve for this, it's actually a decent number that are not so easy. So besides just having stable power and reliable networking and performant cooling, you also need to take care about things like physical security, making sure there are no breaches there, or even stuff like having enough room. Because it's not enough just to kind of fill your data center. At some point, after 3-4 years, some technology might be obsolete. You need to change some of these components without interrupting service, and you need a room to have enough, you need to have enough room to put in the new stuff next to the old stuff, and that's not a guarantee either. So it could be a challenge there as well. And of course, you got to deal with all the hassle of vendor management and waiting for weeks for your stuff to arrive, and that causes you to have to think about issues like capacity planning in advance and making sure you can also finance all that because you need to pay all this up front. So that needs to be part of the equation as well. And only then do you arrive at the level where you're actually back into software land with dealing with the OS and patching all that and your application and updating that. So there's a lot of things that need to be taken care of. And so at some point, some people decide, well, we don't really want to do all that. We have a lot of responsibility here on our plate. It would be fantastic if we could offload some of that. And so the first step there was basically to say, well, why don't you guys take care of this? And in the case of the data center, there we kind of established a simple, stable, standard compliance interface. The 19-inch rack, Ethernet, reliable power, and off we go. As long as these things are provided, we are able to get our servers in there, and we're good to go. It doesn't matter what brand the rack is. It doesn't matter how the power was generated. We're absolutely fine. We have got a stable interface. So that all of a sudden, we now manage to offload some of our responsibility onto them. And as I said, they are free to change it as long as they comply with the contract we agreed upon. So the next natural step is to say, well, okay, maybe we can offload a few more things. And so what if we could then get rid of all that and have our stuff, have our servers themselves being out of our responsibility, having the hardware out of our hands, which is our typical root server model, where you will rent a server by the month somewhere, and it doesn't matter whether the main board is from Asus or from Gigabyte, or how they stuck it together, or the brand of the RAM. As long as it fills the performance contract and the other things we agreed upon, we're fine, we'll rent it, and we're good to go. And that's our root server model. So once again, we have here, sorry about that. I think I'm walking around too much for this mic. Once again, here we have a simple, standards compliant interface. What do we have there? It's the clear separation between hardware and software. And so I'm asking you to think about this. Could this be our industry's Edison screw? Could this be something that will help us for a long time? And once we have that, of course, we enable room for innovation above it, because we don't have to concentrate ourselves on these little nitty-gritty details that don't really help our customers. We do not want to deal with the undifferentiated heavy lifting. We want to innovate where it matters. So let's talk about that software part. Once again, let's see where we all stand. So I'm going to ask you all to raise your hands and keep them up as long as the statements that are here apply to you. So, do you have an automated build on your project? All hands? Yeah. Do you have unit tests? One hand went down. Okay. Do you have continuous integration on your project? A couple of hands going down, but most of them still up. Do you have acceptance tests? Okay, we're still about, that's very good, 70% still up. Do you do continuous deployment of your code? Okay, we've got about 5 to 10 hands left. Do you also do continuous deployment of database changes, configuration, and all that? A couple of hands on it's getting iffy. Who's got fully automated infrastructure deployment? A couple of guys down there. Very good. About 5 of you left. Great. Okay, so how does this process usually look like? Well, we've got our source control and we've got our CI system. And what do we do, of course? The CI system is basically our neutral referee on our project, that whenever a change happens in our source control, it will just basically verify that whatever we've checked out is also working centrally. So we kind of check out the latest versions of the sources, we build them, we test them, and eventually we do produce some kind of deliverable. In the Java world, this is typically a jar file, a WAR file, an EAR file. It could be a zip file, whatever. Some kind of package that has a number of interesting properties. First of all, we create one immutable unit. You do not go and alter your jar file after the fact. You just generate it once, and if it doesn't fit or if there are changes, you simply regenerate it after every change, after every commit. And once you've got that, you go about and promote the exact same artifact from one environment to the next. You do not make the classic mistake of rebuilding a separate artifact for every environment, because this basically means that you're running something untested in production. What you've tested in test is a different artifact than you will have running in production. So we do not make that classic mistake. Now, if we look at our stack of what we actually have running on the machine, we have our hardware that's being driven by an OS kernel. On top of that, we do have a number of libraries that are required by our language runtime, in our case, the JVM. We then have an app server, embedded or not, within our app. This delivery process we talked about so far really only deals with the top two layers of this stack. So the big question to you is, why aren't we doing the same for these other layers? Why should we treat them differently? Or we could also ask, if we're not doing it, what could possibly go wrong by not doing that? So let's look at a couple of things that could go wrong. And once again, I'm going to ask you to raise your hand if you've ever had these problems. You installed something on a machine, and then it turns out that some essential piece or other component simply isn't there, and it doesn't work. Well, most of you, so have I. But it's not the only problem. It could be all working perfectly, but you've got something installed under the wrong name, or some directory hasn't been named correctly, and it didn't quite work out. So I certainly had this problem in the past. Or, of course, all the names are fine, but it's still the old version there with the memory leak, and somehow it doesn't work. So that's a very common problem as well. See most of your hands there up as well. And of course, this is a big classic as well. You're missing some execute permission somewhere, or you're unable to read some kind of resource. So that's a big classic there as well. This is actually a picture I saw in a taxi in Thailand just this winter. I thought it was fantastic, so I had to put it in here. And of course, a port that's occupied, you can't start the server. We all know the deal. That's a huge classic, certainly in development as well. It's very common, but it happens on prod servers as well. So why is that? Why aren't we doing this? To be able to understand that, we have to look back at this little picture here, our classic way of doing things. Here we go again. Somebody's got to keep count. We'll see how many we'll manage in 75 minutes. So, we've got our picture here, and this is basically our hardware that we saw, that we got from Michael, and we've got it all there. So it's actually not too bad. We've produced our artifact. We then have some artifact repository. We upload the artifact, and at some point, we are ready to pull it from there and update our app. Not too bad. Except, of course, that reality rarely looks like this. It looks more like this. We have many instances on many environments, and all of these somehow have to be updated, and it all has to work well. So, because what we really want when we have multiple environments is to have them as similar as possible. Because any kind of difference between instances and between environments is a potential source of trouble. So we need to make sure we avoid surprises and that we have a process that's as reliable as possible to go from development to production. And yes, I said from development to production. This also means that our local environment on our development machine should be as similar as possible to the production environment, because this is a frequent source of trouble. Don't even get me started on using in-memory databases versus real ones and then having surprises because H2 accepts 2 queries in the same statement and Oracle doesn't do it, and then bang, it blows up. So there are lots and lots of classic mistakes that can be made there. So we should really go and have something that's as similar as possible. And of course, at some point, we have to be able to create new ones or re-provision existing ones. And that has to be able to be done in a deterministic and reliable way as well. So, all these instances, all these environments, they don't just live like that. At some point, they evolve and they have to be updated. And not just the application, but actually all different layers on all machines. Whose job is that? The system administrator. His job is to make sure that everything stays aligned, that it all works well. Now you see, we've done a few jumps back in time, and we're going to do another one, again about 100 years, to this gentleman in the automobile industry, Mr. Henry Ford, who had this famous quote, "If I'd asked my customers what they wanted, they would have said, a faster horse." And this is exactly what we got in IT. Instead of a system administrator, we now have an automated system administrator, better known as the puppets and chefs of this world that will perform the same task as the system administrator, just a little bit faster, a little bit more reliably, and a little more efficiently. But it's pretty much the same process still going on. Now, if we fast forward back to the present day time, you'll see that we live in a very different world. This is a quote from about 15 months ago at the AWS reInvent conference of 2013. And you really have to let it sink in to feel the magnitude of it. It's just incredible. Every day, Amazon Web Services adds enough server capacity to power the whole 5 billion enterprise Amazon.com was in 2003, weekends included, again and again and again and again. The amount of capacity that comes online here is just unreal. But that's not the only thing that the cloud brought to the table. What we have here is a clean separation between, on the left-hand side, the control plane, and on the right-hand side, the data plane. So this here is a nuclear reactor. This is the control room. These are the fuel rods. And basically, in the control room, you press the buttons, and this is where all the processing, all the reactions are happening. And so how does this look like from a cloud perspective? We have our admin console, for example, and we've got our instances running, and all of that just kind of works. So this guy configures and provisions basic building blocks on that side, whether it's instances, storage, or whatever we choose to use. And of course, the big innovation of the cloud business there is that this can now be driven by a machine. We can now do this without manual interaction. It's all API driven to bring new capacity online and turn it off again, which is something that has never been possible for an on-prem solution where you can just pull the plug and stop paying for it. So this is really quite an interesting innovation that we have here, because all of a sudden you can start thinking about a billing system that runs at the end of the month for 5 hours, and you pay for 5 hours. You then shut it off again and it doesn't cost you anything until the end of the following month. So it's actually very interesting what we've got here. So we have shifted from a world of scarcity to a world of abundance as far as our resources are concerned. And we'll see later what this means when it comes to updating applications and the possibilities that this creates. we have, for the first time, a control plane that can be driven by a machine to provision the data plane. So that's a very interesting thing there. And we've got our architectures that we can now start shaping based on the expected cost of the resources we have in use there. So in light of all that, I believe it is time to rethink our faster horse. If we now really consider this piece here, our hardware, as undifferentiated heavy lifting, as long as we have a clear contract there, we are able to exchange it. So let's exchange our physical hardware for virtual hardware. And suddenly, new possibilities arise. We do not need to produce a classic artifact anymore. We can start producing an image of an entire machine, which can be uploaded to an artifact repository and being deployed as one immutable unit. So that we then move from a world like this to a world like this, where if we write our machine images and our infrastructure correctly, and if we comply to our contract, we are even able to run on multiple types of virtual hardware. The updates that had to happen at the individual instance layer now vanish. Instead of that, they're all pre-baked in the image, which can then be promoted from environment to environment unchanged. No need to rebuild it every time. Take the same unit and deploy it from one to the next. But of course, most of you are thinking right now, we have one big problem left. Our machine image is actually pretty large, and our network pipes haven't kept up. So it is expensive to store thousands of versions of a machine image over the course of a year. It is complicated to transfer all that over the network. It takes too much time, it is not practical, so how do we deal with that? Once again, let's turn to some wisdom. This wise man here once said, running servers in production should be like going backpacking. You take the bare minimum with you, anything else is going to hurt. So once again, one of my own pictures here from the Bavarian Alps, where we were ready to walk up the mountain an early summer morning, I think about 2 years ago. And these guys are coming down from the mountain. They'd gone up with a 20-liter wooden keg of beer, like the 4 big glasses, the hammer to open it up. They basically drank it all on the one evening, and we're coming back down. So total inefficiency. And somehow, that's how we run most of our servers. We've got like a 20 megabyte app and we carry around gigabytes of stuff. And so if we are going to prune some of that fat, we should have some objective criteria to decide what to keep and what to leave out. And for me, the real criteria here is what is actually helping my customer? What is adding business value and what is just technical ceremony? So, to be able to analyze that, I'm going to pull up my X-ray machine and we are going to look inside the machine image. What we have here is a bunch of components. There are actually more on the real machine. This is just a bit of a selection of what we have there. So let's start analyzing. Our application, we're going to keep, because if we don't have it anymore, there's no reason for our customer to pay us, so let's keep that around. But do we need compatibility with old binary formats, with 32 CPU architectures and all kinds of obsolete things? Probably not, if the only thing we want to run is our app. We will keep the app server, because our app most likely needs it, but has a man page ever helped my customer? I don't think so, so off they go. Has a customer ever been excited about the fact that you had apt-get installed on your server? I don't think so. So off it goes. We will need our language runtime because we actually need to run our server and our app, so we'll keep that. But if I have a Java, a Scala app, do I need a C compiler on that machine? I don't think so. Off it goes. It is 2015. I believe the times of having 5 different consoles open and tail-F of different log files is not something that belongs to this century. And so neither do the log files on the machine. Off they go. If I haven't got any log files on these machines, do I need a VI? Do I need an Emacs? What for? Do I need all the other random utilities that are usually hanging around there? No, I don't. And if I don't have any of these things, why would I even need to log in? No need for SSH. And if I can't SSH, no need for multiple users. Do I even need a firewall if the very things I set out to protect simply aren't there anymore? Off we go. Do I need a shell? Probably not. Do I need drivers for thousands of pieces of hardware when all I need to support are a few virtual network cards and other pieces of virtualized equipment? No, most of them can go. I'll keep a few libraries to make my language runtime work, but a bunch of other random daemons that are hanging around there are not needed either, so we'll just keep the OS kernel to drive our hardware. And what we have here is actually the bare minimum that's actually adding business value. That's the bare minimum our app needs to run. And so if we fuse all that together, we get what we call a bootable app. And we are now in a very different territory compared to our machine images. For the JVM on Java 8, this is about 40 megabytes plus the size of your app. And that includes everything from the bootloader up. So that all of a sudden, the issues we had with storing thousands of versions of this per year or transferring it over the network just vanish. It becomes very fast. Now, I'm sure a number of you are thinking right now about all kinds of cases where this doesn't apply. It doesn't matter. For every really special case, there are many more that are just ordinary business problems needed to be solved. And so the typical use case for this is the 12-factor app, the microservice, the app that doesn't have state on the middle tier. So let's have a look at this in practice. For that, I'm going to use our company's software, BoxFuse. So what I've got here is a small sample app. It's the actual text doesn't really matter. The ones at the back will just have to believe the ones at the front that I'm going to modify this and just to show you that this is all live. So let's just say, hello, Devnexus. 1, 2, 3. Up, save this guy, and I'm going to rebuild this app. So just, so it's a Maven project. So I'm just going to do a Maven clean package. Just going to have that running. Should take a few seconds. Beautiful. Doesn't matter. I'll just skip this test. It's the beauty of demos. What wouldn't they be if they wouldn't fail? I think we already have our artifact anyway. Doesn't matter. I've misconfigured the Surefire plugin, so it pulled in the acceptance test in the regular tests, but that's okay. But it's okay. It's good proof that it's all live, ready to live on the edge. So I've got a WAR file here, and what we're going to do is we're going to fire it up locally. We're going to turn it into a bootable app and get it running locally on VirtualBox. First of all, so to do that, it's BoxFuse run, and we point it at the WAR file, and off we go. And so what is happening now is that we do have a bit of analysis that has taken place in the background, where basically kind of sniffed out the type of artifact we had there. We found out that it was a WAR file. A WAR file requires a Tomcat requires a JVM requires a C library requires an OS kernel, and off we go. So these are all just defaults, and by default it's just kind of picking up the latest version of this, but that's all okay. So that took about 10 seconds to bring all that together into an image that's about 48 megs here. You have to remember this is a laptop with a native VGA port. It's actually from a museum, or it could be. It's from 2010, so on modern hardware it's about half the time. And then we launched a new instance of that. We forwarded a port on localhost. We then waited for an HTTP 200, which has been returned, and we then got the URL here. So we're just going to copy paste this guy into the browser and see what's up there. And so here is our brand new, fully hardened machine, which we just created a few seconds ago. So it's this is just a bit of a sample app that I built, where we've got a couple of things, but we can look a bit behind the scenes to see what actually happened there. So what we have here, first of all, is we have BoxFuse LS that lets us look what we have. So in this case here, we have one image that we've generated. This is still European time, so that's what it is there, where we've got a Tomcat 8020 Java 8U40 in there, and the whole size of it is 48 megs. And if we look at the processes we've got running, so the instances on VirtualBox, we should have one guy up here with the ID VB blah 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 that by default has the same number of CPUs as the host, and a gig of RAM that's all configurable, and it's running at this address here. So what we can do is look at the logs for this guy. So we'll see how it booted and how that all went. So I'm just copying this here. And if I kind of scroll back up, you'll see this is kind of the box starting, and we're picking up an IP address through DHCP, and then we're kind of dumping some kind of summary of what we've got on board, our environment variables, and this is just a regular Tomcat starting. So it's basically our app up and running there. We can also just kill this guy. It'll just kind of shut down. We'll preserve the image, but it just shuts down the instance on VirtualBox. But much more interesting, and if you thought that the failure of compiling and having the tests running was already pretty brave, well, let's try to get this guy up on AWS live on stage. So I would say, don't download anything, don't upload anything. I'll need all the bandwidth I can have for this. So this is really, there's no net, there's no nothing. So we're going for a full risk, but it's okay. That's part of the fun. So let's do it. BoxFuse deploy. I've configured this in the console to be in the EU Central 1 region. And so off we go. Just gonna fire this guy up. So you're seeing we haven't regenerated any image. We just took the existing image. Come on, network, come on. Yes. Shall we? Yeah. Shall we? Yeah, we'll wait. I will make it happen. It should be another minute. We should be go. So basically, we've reused the same image. Nothing's been generated anew, and now it's being pushed out to our centralized infrastructure, which we call the Vault. It's just some kind of secure remote repository for images, and then from there it will get transformed into an AWS specific format, the AMI, the standard image format on AWS, and we'll kind of spin up an instance, assign a domain name to it, and all the other fun stuff. So let's give it a couple of more seconds. It was very fast this morning, but I guess maybe in the room next door they're all doing some stuff there. So let's see. It should be good. All right, 40 megs down. Come on, don't give up. This is the part that my girlfriend can never understand. How could you get excited looking at some black and white window like that? You know, oh well, you won't understand. It's an IT thing. Anyway, it's gone up and running. It's been uploaded. We've validated it cryptographically to make sure it's got transferred fine. We created an elastic IP, which is just a fixed reference point in the AWS infrastructure. We've mapped a domain name onto that elastic IP. It's right here. It's hello-axelfontaine.boxuse.io. We have then commissioned AWS to create an AMI from the image we have there. So that took about 26 seconds here. It's mostly waiting for them to kind of do whatever they're doing. They're probably scrambling for cables and quickly passing over some diskettes to copy something. I don't know how it takes that long, but anyway, that's a mystery only AWS can solve. And then we have created a security group that is some kind of external firewall where you just say that these network connections are allowed to reach the instance or to leave the instance. So in this case, we've by default taken port 80 from anywhere that we've allowed there. And then we've launched an entry medium. It's just some regular general purpose instance of our image that took about 16 seconds. And then we waited for our HTTP 200. Once again, we have then remapped our temporary IP address to our elastic IP address, and now everything is up and running at this new domain name that just got created right now. So once again, let's go to the browser and copy this guy. Here we go. That's still something old. There we go. Hold on. We do have, there we go. There was some DNS caching issue. So that's our app up and running on AWS on a brand new image that didn't exist 2 minutes ago. And it's identical, bit for bit, to the image we had running on our machine. Now, this is all nice and well to do manually. But the real interesting part is, of course, integrating something like this in a delivery pipeline to make sure we don't have to do these steps every time. And so to do that, we have build-tool plugins that let you do that. So in this case here, it's a Maven project. So I'm just going to re-enable a couple of things that I disabled before. So it's basically, I'm just re-enabling this, and I'll go back up. What we have here is I re-enabled two different plugins. We have the BoxUse plugin itself, which executes 3 different goals. It executes the run goal, which by default runs in the pre-integration test phase. So before we're going to run any integration tests, then we have a kill goal that will run in the post-integration test phase to shut things down, and we have a deploy goal to push it out to AWS. And then here we have our Surefire plugin configuration, which should have excluded our acceptance test before, so I don't know why it wanted to run. But anyway, we'll see. And we have our failsafe plugin here that runs, and that by default is taking one environment variable here that's dynamically assigned that is basically the URL of our instance, so that our test can then find our instance no matter where it is and connect to it. The acceptance test is something very simple. Here it's HTML unit. It just basically kind of pulls up the web page and checks that the text we wanted is there. So we've got version 1.0 deployed already. So let's make some change and call this 1.1, and we're going to change hello Devnexus from our automated CD pipeline. Up with a bit of a change here, and off we go again. So this time we're not going to call that, we're just going to go through Maven, and since we've bound all these different things to different phases, we are just going to call Maven clean deploy, then hopefully all work. So once again, don't overload the network. We'll see. Here we go, building version 1.1. That's all good. So we're building an image to run locally now, just as we did before. Kind of just assembling the different components into one bootable app. Takes about 10 seconds on this machine. Here we go. We've fired it up. We've forwarded a port. We're waiting for HTTP 200 once again. We're now running our acceptance test against it. That passed, so we're shutting down the instance. This is going well. We're pushing all this to the vault. We need some kind of a little bit of a drum roll here for the music. Go again, scroll bar excitement, progress bar. So the idea basically is that this is something that you set up once and then you never have to worry about it again. Just for every build, it'll just kind of run. You'll test it on the exact same machine as you will have then running in production. And if these tests are successful, you push the same machine out bit for bit so that it's absolutely identical. And you have it running up and there in usually, to get the instance, it's about 60 seconds and then a bit longer for the app to boot, depending on what you've got in the frameworks you've got on board. And if you've got Spring and Hibernate and all that, it takes a bit longer, but that's then just kind of depending on the app. So let's see here for AWS to bring all that on board. 25 seconds, that's good. Launching our instance. Off we go. Couple more seconds. Here we have it. Waiting for an HTTP 200, and it's going to do the switch. Okay, could actually pull up the browser, and we're going to reduce the size of this a bit. So now we're in the process of remapping the Elastic IP. So we're still touching the old box right now. We're on the new one. So the domain name has been switched. Well, that's still stuck to the same Elastic IP, but we switched over to the old one, terminating the old instance, and all that just kind of happened with zero downtime. So I'm just going to shut down the old instance now, and it's just a couple of seconds more. Not that interesting. So let's go back to our presentation. This is a very different model than just connecting to existing machines and updating a piece of those machines, updating our software or updating one of these layers. So there are a number of interesting implications of doing things this way. The first one is that we have a strong focus shift, where before the instance used to be a central piece, now the focus really shifts to the service as a whole, where we really want to make sure that the service is available and not the individual instance. That is what we care about. Individual instances themselves become a disposable artifact. So the famous saying, of course, treat servers like cattle instead of pets. So who has ever given their servers a name? Oh, all of you? Well, it's going to be brutal times because this is how we're going to treat them, and that's still okay, but at some point, just as we did here, a new version will come around, and so what will happen to these guys? It's a cruel world. And so this kind of brings us to an interesting topic, where there used to be this time in the IT industry where people used to pride themselves of having incredible uptime for their machines, as if it were a good thing. And I'm saying this is incredibly dangerous, because the longer an instance is up, the harder it becomes to recreate it exactly the way it was. If it ever dies, and trust me, at some point it will fail. whether it's the hardware below it or some update in the software that causes it to get corrupted or whatever it is, at some point you will have to go through this exercise, and it becomes exponentially more difficult the longer this instance is alive. So uptime is a liability, not an asset. So if all these pieces of our infrastructure are ephemeral, if they just kind of come and go, we have an interesting problem with service discovery. How do we do that? Well, we can solve that by using a stable entry point with an internal registry. In the case of our example here of our little demo, it was an elastic IP that we tied to a domain name. But the more usual thing on AWS at least is simply to have an elastic load balancer. The elastic load balancer will itself keep track of what instances it is load balancing the traffic to, and we'll just kind of send the requests to them, and if new instances come along, it'll start sending in requests to these ones, and it'll eventually take these ones offline, and our clients don't have to know. All they have to know is the address of the elastic load balancer, and the rest is taken care of. There is no need for real, large, complex solutions here. This works very well, it's very reliable and very fast. The other very, very interesting implication of this is security. Or, to rephrase the question, when was the last time your toaster got hacked? We have reduced the attack surface to the absolute minimum so that all this potential for trouble just kind of automatically vanished. And that's not the only thing. If somebody does break in, the consequences are most likely much less severe than they would be on a traditional machine for two reasons. Number one, this machine is short-lived, so whatever has been Trojanized there will not live along a very long time. But the other thing is that simply the tools you would use to further penetrate your network simply aren't present on these bootable apps, so that you can then not go about and exploit all the other hosts in your systems. It's actually very interesting. The other big thing, of course, beyond the simplistic little hello world thing here I demonstrated, is configuration. There, the big thing is that when I do my continuous delivery talk, I spend a bit more time on this subject. I feel that the important question to ask when it comes to configuration is a question of life cycle. What is the life cycle of my configuration? And usually we find that there are two large categories of configuration being available within systems. The first one is stuff that could potentially change someday, so we decided to make it configurable, which is really just a backdoor for an inefficient release process where we can just quickly go and change something on the server, because if we would go the regular way, it would take too long. And of course, the genuine differences between environments being the second type of configuration. Now, for these genuine differences between environments, there is actually a strong correlation between the life cycle of that configuration and the life cycle of our app, where in a certain version of the app, we may need to connect to the database, and in the following version, we need to connect to the database and the messaging system. And so it's actually tied to a certain release of our app, what our requirements are there. And so I strongly recommend to really go the route of including as much configuration as possible directly in the app and designing an algorithm that will let you choose at runtime automatically which set of configuration to pick. And this is basically just saying, okay, what is the simplest possible way for me as an application to determine where I am? And this could be analyzing IP ranges or host names, or simply maybe just a property that gets passed in that says, well, you are in development, you are test, you are production, and then just reading out the correct property file and configure yourself automatically for that. Now, in a number of environments, this is not possible due to certain trust issues with some sensitive pieces of configuration. Now we're all thinking about passwords and that type of stuff. And so it may be necessary to pass some configuration in from the outside. And so to do that, all modern hypervisors lets you pass in a little bit of data on instant startup. And so you can use that to pass in key value pairs that then get exposed as environment variables, and you can then read them out at runtime to behave like your app would like to behave in that environment. Now, at some point, we also want to deal with a bit of state. We want to actually store some things and deal with them. So how does a database fit in all this? If our instances are disposable, being thrown out as soon as a new version comes, how do we do this? Well, the key is to keep the database out of the instance. In fact, to keep all the state that you can, all the persistent state, that is, keep that out of the app and have it somewhere else, whether it's a regular database server or some hosted service somewhere. Just have it out there. And if you do need to upgrade the structure of that database, if it's a relational database, you may need to add some columns to some tables, rename other things, create some views, indexes, whatever. That's where database migration tools like Flyweight come into play. I highly recommend to run them on application startup. Once again, we have a lifecycle question there, and that is, what is the lifecycle of our database structure? And I, once again, think it is very tightly coupled to the lifecycle of our application, because in a certain release, we will have, for example, Hibernate expecting with the JPA entities to have a number of tables and columns present, so it can then read and write from those. And in the following release, these expectations might have changed, where we have new fields that have to be written or read. And so we have to make sure these things stay aligned. And why would we then go about to separate them and take the risk of not having them fit together at runtime? So in that case, I'm really saying, put the database upgrades in your bootable app and run them on application startup with a database migration tool that supports an API if possible. There are, you can run your own database server. There are also very good hosted options these days, whether it's Amazon RDS or Google Cloud SQL, or on Azure if you're into SQL Server. All that works very reliably, and so all of these just kind of work with any kind of modern database migration tool. If you like to hear a bit more about this subject, as I said, we're going to dive into this a lot deeper tomorrow. In the morning, we will have a look at how this fits in a continuous delivery pipeline, how to do all this in a backwards compatible way, solve all kinds of challenges with this. So if you're interested in that, we have our session tomorrow. The next big thing, of course, is the logs. We briefly touched upon them, that tail-F in many different windows is not something for the 21st century anymore. So once again, here we have fantastic offerings there, and I'm saying in the 21st century, you ship your logs to a central log server, and that brings you a number of advantages. You can then have your logs nicely aggregated in a place where they can then easily be stored, backupped, indexed, and be searched through a nice web UI. Most of the common tools available, like Loggly, Logentries, Papertrail, or whether you build your own with Kibana and Logstash, or if you're into Splunk, and they're all even offering you a lot more with some alerting systems and all that sort of. So that's actually very nice, and it avoids the need to kind of open up unnecessary ports on your machines to be able to log in and do all that. It's just kind of shipped out. It can be via UDP or asynchronous via TCP and SSL. So there's lots of good solutions there. I highly recommend to have a look at any of these, and you can all get started for free. It's quite nice. The sessions. The sessions are an interesting thing as well, because traditionally in the JVM world, we've gone very wrong about this. We took many approaches that just went down the wrong path. And all we would have needed to do was to look a bit around us at what other platforms were doing, at what even our friends from Microsoft, at ASP.NET, or our Rails friends, or to a certain extent also the PHP world is doing, and that is to store sessions in the cookie. Now, you really want to keep your session data as small as possible anyway, because the reason you have a session is basically to identify who the user is. There is not much more that should be kept in that session. So keep it as small as possible, and if you have it in a cookie, you can encrypt it and cryptographically sign it to make sure that it's not readable and that it's not being tampered with. There are very good tools available for this on the JVM. There is a servlet filter that you can just plug in, and then it transparently does this for you. So that from an application perspective, you work with the servlet API as you're used to, and you simply have your request.getSession and blah, 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 and that all works the same. But as you send the response, it will serialize the session object in JSON format. It will sign it and encrypt it and ship it out. And as it comes back, we basically go the other way. We rehydrate it, we convert it all back into our regular Java objects, and we can work with them as before, transparently. So that's definitely a route I encourage you very strongly to go to, because it solves a bunch of annoyances that we've had with this in the past. Session timeouts. Why do we have session timeouts? We don't just have them for fun, for the pleasure of annoying our users. There's actually been a good reason why we've had session timeouts, and that's memory consumption. Because every session just kind of eats away a little bit of your memory on your server. If that memory is not there anymore, if it's in your cookie, instead of having to keep it around on the server side, all of a sudden, you are now able to size your infrastructure for the number of actively processing requests and not the number of open sessions, so that this can have very interesting implications on your memory requirements. And you get rid of the annoyance of expired session for your users. You can get rid of all these terrible ideas we had of clustering and replicating sessions and electing peers to do all that. All this complexity just kind of goes away. You can start farming your machines. Any of these machines can die at any time, and it doesn't matter. The request gets picked up by another machine, the cookie gets decrypted, we validate the signature, we hydrate the objects, and we're good to go. So all this is not necessary anymore. You can get rid of all that complexity. And I think this is a bit of a big theme for this talk today, is that there's inherent beauty in keeping things simple. And I strongly believe in that. And this is certainly a point that supports that very well. And so another aspect you can get rid of is all the stress this puts on your load balancer. When you do upgrade your software and having all the classic sticky session serve and affinity solutions where the load balancer has to keep track of which request was being sent to which server in the past and always deliver it there because the session's always there. So that lets you get rid of that as well. You don't need to worry about that anymore. So we already saw in the demo how that all worked with rolling new versions out, but let's have a look at it from a diagram perspective as well. So we've got our app version 1 in the cloud world to ensure it's actually reliably there. When we send the request, we don't just have it sending it to the app and it'll send it to the database, but what we actually have is this concept of availability zones, which is basically just one data center in one geographical location, and then you have multiple of those so that in case of a disaster, you are then redundant as far as that's concerned. So you deploy your app across multiple availability zones, you load balance the requests between them. As we saw, you can simply farm them, no need to replicate any state between. It's all good. The state is either in the front in the cookie or in the back in the database. We have got our logs that we all ship to a central logging server where they're aggregated, they're being stored, archived, indexed, made searchable. And then at some point a new version of our app comes along, so we deploy. This is where we touched upon with our world of abundance. We are not limited by the number of machines we can fit in our rack. So we just deploy it next to the existing one, like we did in the demo as well. We just kind of spin up new instances. So this is the classic expand and contract mechanism where we temporarily double the size of our infrastructure, and we make sure these new instances are healthy. And when they're healthy, we start setting traffic to them, and we take the old ones offline and undeploy the old ones. Then we contract our infrastructure again. So this has some cost implications, but on modern cloud platforms, when you just have a 1 hour or less overlap between them, this is in sub-dollar amounts we're talking about. So it's really something that also has never been possible like that with on-prem infrastructure. So the elephant in the room, I think, is also what some people asked me before the talk. Is this about Docker? How does this relate to containers and what's around there? So let's have a look how these different techniques relate. But to better understand that, we have to look at how modern CPUs work and what type of interesting properties they have. So all modern CPUs, whether from Intel or from AMD, have hardware-level support for virtualization. When this was first introduced, this was a means of isolation to make sure that basically one guest could not invade the memory of another, and there would be proper fencing there. And as the processes have been improved over the years, other mechanisms have been put into place to compensate for the performance loss involved with that isolation, where we now have virtual directed I/O that kind of pierces straight through the hypervisor to the disk or to the network, and we have all kinds of interesting things now there to kind of limit the impact of isolation. But isolation is still there, and it's a very valuable thing. And so once again, think about the beginning of this talk, about our Edison screw, and how this is actually enabling multiple Edison screws on the same processor. So if you have our classic virtualization stack, where we have our hardware, our hypervisor, and in this case our bootable app. If this wouldn't be a bootable app, this would be an OS plus whatever other things you would have in there. The main point is, this is fenced in hardware at the processor level, so that you cannot escape that box. If we look at the container model, this is what it looks like. So we have our hardware, then we have our operating system and our container runtime or engine, and then we have our container running on top of that. There's no fencing there at the hardware level, but it may not matter, because if you are on-prem, you trust your neighbors. You will not have an evil competitor that will try to Trojanize your box and steal some trade secrets there. That will not happen. So you do benefit from the lack of isolation, actually, and being able to go straight through and not having all this fencing. However, as I said, you have to trust your neighbors. If you bring the cloud into play, you don't know who you're sharing the box with. And that's the reason why every single container solution of the cloud players today is running within VMs. Whether it's the EC2 container service or the Google offering, it's all the same. You do want fencing around that at the hardware level to protect from badly intentioned neighbors. So there are some use cases for actually having this model here, but I kind of say that they're a bit narrow, because a T2 Micro instance on demand, the most expensive you will ever pay for it, is $9.60 per month. So that's the granularity we're talking about here. So it could be that you have certain cases or certain economic realities that cause you or that force you to subdivide that into smaller units where you need more efficiency. That's possible. But you have to think about it very carefully, because remember our very nice separation between data and control plane. All of a sudden, you have a second control plane here, where you then need to manage your own containers within your pool of instances, and you need to start worrying about things like capacity planning again and making sure you have enough of your own instances in your pool for the EC2 container service to make it work. So think about this very carefully. $9.60 a month. Or, if you think about cost-based architectures and a more dynamic thing, 1.3 cents an hour. This is really the granularity we're talking about. And so, that's the question you should ask yourself. Is 1.3 cents an hour too much or not? Or can you simply live with that, even if a few megabytes of RAM might be unused? So, let's summarize. We have seen that for our classic CI pipelines, we in the industry have found it very valuable to produce one immutable unit that gets regenerated fresh after every change, and that we then promote unchanged from environment to environment to avoid the classic mistake of building it anew for every environment and ending up with a different environment in production than the one you tested in test. And we now take all these principles and apply them for the entire machine at the bootable app level. So it's basically just taking everything we've learned and appreciated and including the other layers to avoid all the problems we saw before. Now, I am a very strong believer, of course, in this concept. I believe we will see within the next few years the end of the general purpose operating system for our service. And I also believe that the provisioning as we know it today is something that will disappear. You are more than welcome to implement these concepts yourself if you are on AWS and if you are on the JVM and what I talked about today resonated with you. I highly encourage you to sign up for our beta list here at BoxFuse. We are going to launch this month. So whether it's interesting to you or not, I leave that question open, but you're more than welcome to have a look. This is my Twitter handle. I'm Axel Fontaine. My Twitter handle is @AxelFontaine if you want to get in touch or if you want to follow me or kind of ping me for something. We have a talk about Flyway, as I said, tomorrow morning, 10:30, where we go into a lot more detail about this. And otherwise, that was all I had for today. Thank you very much. I think we have 3 minutes for questions. Anyone? Yes?
So all the examples that you gave were Maven-based. Is this a Java-only technology?
So the question is, all the examples were Maven-based. Is this a Java-only technology at this point? The primary platform we're targeting for launch is the JVM, but you are not tied to Java, the language. You can use whatever language you fancy for that and whatever build tool you want. Any more questions? Go ahead. So
I'm sort of inferring here, but it seems like the BoxFuse solution includes its own cloud controller. Is that basically or it can be ported to various providers?
So the question is, it seems like the BoxFuse solution includes its own cloud controller, or does it have to be ported? So at this point, it is indeed two parts. So the first part is generating the images and being able to run them locally, and the other part is the cloud orchestration. And our primary target for now is AWS, but it is in no way tied to AWS, just like it is in no way tied to the JVM. So it's just a place where we'll expand from over time. Anybody else? No. Okay, well, if there are no more... Or,
I had a small question in my
sure.
specific way. You were talking about basically just storing sessions in the cookie instead of storing them in a more central place. So, like, does that even like preclude like having a central session server? Like, how are you trusting what's actually stored on the user?
So the question is about sessions in the cookie, and how do you trust what is stored in the, on the user's machine, or what is being sent to you? And so the answer is that you do have cryptography to help you there, where you can then with public-private key infrastructure sign all that, so you can make sure that the signature validates when it comes back, to make sure it's not been tampered with, and you combine that with encryption to make sure it's not readable. And with the current processor technology and AES 256, we are good until at least the next 30, 40 years for that. So there is, at least to the best of the knowledge of the industry, it should be safe. But there's never a guarantee, of course, on that.
Besides Amazon Web Services, if we use private hypervisor, which is API compatible with AVMs, can we run that thing? Or can we just use it for image preparation?
So besides classic AWS, if you run your own private hypervisor that is API compatible with AWS, I'm guessing Eucalyptus or something similar, can you use that as well? We haven't tested it, but we do have for our own testing infrastructure. We've kind of rebuilt the whole of AWS as well from an API perspective to be able to test that very quickly. So I assume that if it's truly compatible with AWS, the changes that would be required to make it run there would be very minimal. So we can definitely talk about that.
Yes. So when it builds the pruned image, what's the starting point for that? Is there an image that's provided or chosen by the user for that?
The question is, what's the starting point when you build an image? Is there some kind of base image chosen by the user, or how does that work? No. We start from scratch, just like when you build a WAR file, for example. You kind of just assemble the different pieces, you pull in the libraries and kind of your classes and all, and it's the same principle here. So we just start from a blank disk image in that case, and we just kind of throw everything in. So there is no Ubuntu or Debian base or whatever other classic OS. All that is not part of the mix anymore. Okay, well, if there are no more questions, thank you very, very much, and enjoy the rest of the day.